Alright, and the last major concept in this chapter is buffers. Now, I want to first relate to you what the word buffer means in everyday life first before we talk about what it means in chemistry. For example, you may have heard of terms being used like this will buffer the attack, as in like this will make the attack less impactful, right? Or this is a buffer zone, meaning that this is a safe zone. So buffer used in all these contexts is related to how it is used in chemistry. So in chemistry, a buffer is a solution in which it prevents the change in pH upon addition of acid or base. Right? So that means if you have a solution, if you add more acid into it, it would not change, it would not decrease the pH level dramatically. Or if you add base to it, it would not increase the pH dramatically. A buffer will make change, but very, very little. It will try to resist as much as possible to any change in pH. In order to illustrate how this works, let's imagine a beaker of solution. Alright, so in this beaker of solution, you have only water. If you have only water here, your pH should be pH of 7, right? This should be pH is equal to 7. Now let's imagine what would happen if we would add in acid into this solution. Let's add in HCl. As soon as you add in HCl, remember HCl is a strong acid, so it will dissociate completely, giving you H plus and Cl minus. Because you have added HCl into water, you have generated a lot of H pluses, meaning your solution would now become more acidic. So your pH will then decrease dramatically. Now let's see what happens when you have a buffer in there. A buffer is made of a weak acid and its conjugate base, or a weak base and its conjugate acid. Let's take one of those examples right now. Let's go with acetic acid. Remember, acetic acid is a weak acid. Alright, so this is acetic acid, and recall it is a weak acid. Remember how to write acetic acid dissociating in water? Remember the H in front is your acidic hydrogen, whereas the hydrogen in the middle are not acidic. That's why we try to differentiate them. Right? So if this was your acetic acid, and if you put this into water, we usually write that the hydrogen will break up, and your acetate anion will result also. Okay? But by definition, a weak acid does what? It actually goes backwards like this. So most of the acetic acid that you put into your solution is mainly in its acid form, not its deprotonated form. Right? So let's put in this acid. And again, the definition of a buffer is its weak acid plus its conjugate base. And what is its conjugate base? It's this guy, right? So then we can also plus in C2H3O anion. Now, of course, to be more practical, anions cannot exist by itself, so we actually have it as a salt of sodium acetate. Right? So again, weak acid and its conjugate base, salt, Na, or any kind of lithium, sodium, potassium, any kind of counterbalance cation. Correct? So let's imagine that you have that in solution here. And I'm going to now abbreviate this as A minus and this as HA for convenience. HA for acid, A minus for its conjugate base. If we have a bunch of HAs in solution, an equal amount of A minus in solution, let's say that, right? Would this solution still be neutral? Right? So to simplify it, let's just say it is. And how do we know it is? Because we don't see any hydrogens floating around by itself. Because why? Because acetic acid is a weak acid, so it will generate that hydrogen by itself, but mostly it will stay as an intact molecule. So you only see HA and A minus, no H pluses hanging around, correct? Alright, now we are ready to put in our acid to see it will resist the change in pH. If we add in this hydrogen chloride, the first thing it will do, it will break up hydrogen plus and Cl minus, right? So you say, you did increase the concentration of hydronium. But it turns out though, remember that acid and base will react with each other? you have your conjugate base here and your acid here. So what will happen? If H plus sees A minus, what will happen? H plus sees A minus, what happens? It forms HA, right? So this guy gets eaten up by that A minus to form HA. Voila! Do you see why this is a good buffer? Even if you add in HCl, it will resist the change in pH. You see that there is no more or less H plus hanging around because you have this guy protecting it. Alright, so we have just established that acetic acid with sodium acetate will give you a good buffer against acid. Now, a true buffer also protects against addition of any strong base. For example, if now, so let's go back to our original case here of our, of our buffer. Now, what's a strong base we could add? We could add NaOH, right? Sodium hydroxide is a strong base. Once we add that into our solution, first off, it will break up into Na and OH minus. If you have a lot of hydroxides in your solution, you would usually call it a base, right? A basic solution. Therefore, the pH you would expect to increase to become more basic. But watch what happens. This OH minus is a base, and HA is an acid. HA, when it sees, so again, this is your acid, and this is your base. What happens when an acid and a base seize each other? Based on our previous section, we know that acid and base will try to react with one another. Right? So this base will take, what is the job of a base other than to take an acid, right? A proton acceptor. Once it accepted that proton, it becomes HOH, and HA is a proton donator, so it now gives away hydrogen to be only A minus. Okay, so let's see and erase. So let's see what happens now. With that OH gone and that HA gone, what do we have in solution other than H2, HOH and A minus? I slipped there, right? What is HOH? HOH is none other than H2O. So have we dramatically increased the concentration or dramatically increased the pH, making it more basic in the solution? We have not, right? Because all we see now is that you have water, which is neutral, and A minus, which is not hydroxide. Alright, so we have proved to us here that a buffer resists the change in pH because it has one component, the acid, that will react with any base you add to it, for example, OH. And it also has the other component, the conjugate base of that weak acid, to react with any acid you add into it, the previous case of HCl. Okay? So what's the take-home message here? You either have a weak acid, its conjugate base, or a weak base and its conjugate acid. Let me give you some more examples to clarify this concept. Okay, so if I ask you to come up with a buffer system, again, what do you need to do? You need a weak acid
plus its conjugate base, salt, or a weak base and its conjugate acid, salt.
Alright, we just gave an example of this, was the acetate, acetic acid, and sodium acetate. Now let's try to think of how do we make one that is from a weak base. So what's one weak base that you know off the top of your head? One easy one I know is ammonia. Okay, ammonia is a weak base, not a strong base. Basically, any hydroxide, OH, is a strong base, like sodium hydroxide, potassium hydroxide. Whereas anything else that is a base is a weak base. What do you think would be the conjugate acid of ammonia? Remember from that section in the previous videos, how if I give you a molecule and ask its conjugate acid or its conjugate base, you should be able to do so. So what is the conjugate acid of NH3? The conjugate acid of this would be as if this reacted as a base, right? So if this reacted as a base, it would accept a proton. If it accepts a proton, it becomes NH4. And what's the charge there? Remember that a proton is not only a hydrogen, but a hydrogen positive. So you gain a positive charge there. So again, the weak base here is ammonia plus ammonium ion. Okay, I said salt, right? So this is a positive. So what do I need to balance it out with? An anion, right? Since this is a cation. So what's a anion that we know? Chloride, right? So we can balance this out with chloride. So positive and negative cancel each other out. So you would say that the salt is ammonium chloride. So this gives you a good buffer. Alright, so let's do a checkpoint to flush this idea out. Which of the following is a buffer system? Okay, the first one says NaOH. So I want to analyze each of these chemical compounds to see if they fit our criteria of a weak acid or a weak base and its conjugates, right? NaOH, is that weak? First of all, is it acid or base? It is a base. And is it a weak or a strong base? It is a strong base, right? So therefore, off the top, A would not be an answer already. Is it a strong base? Next, B, KCl, is that an acid or a base? Does it have an OH in it? No, so it's not a base. And it has a cation and an anion, so it's an ionic compound. It doesn't have any protons, so it's not even an acid. So this is just a salt. Right? So let's move on to this side. NaCl, is that an acid? It doesn't have protons, it's not an acid, and it again is a cation, anion, so it's an anionic compound. So again, it's just another salt. Two salts together do not make a good buffer. Moving on to this one, HF. Ooh, it is an acid, and how do we know it's an acid? It has hydrogen ring in front, so that's an acid. But is it a strong acid? It is not, because it's not one of the strong acids that we have memorized. There's only a few, so you should memorize them. So this is your weak acid. Okay, we have one criteria, or is it one criterion met? And if we have a weak acid, we also need its conjugate base, right? What's the conjugate base of HF? F minus, right? Do we have F minus over here? Yes, we do. That's F minus. This is an ionic compound, so this is F minus. This is K plus. So we do have its conjugate base in the form of a salt. So I think this might be our answer. But let's go on to see why D may not be our answer. D, calcium hydroxide. Ah, hydroxide, so we know that that is our strong base. Yep, our answer is indeed C.